Okay, let's we move on to second order reactions. Imagine that this is A, it will produce products, and another example I will write down, A plus B, it will form products. If I write the rate equations for both of these reactions, d minus dA divided by dt is equal K A. If it is a second order, this order will be 2 with respect to first reaction. What about the second reaction? dA over dt, this means rate is equal to K. A and B, there are two participants, reactants. With respect to both, the order will be 1. Order of A will be 1, order of B will be 1. Or we can express it like this also, dt is equal K. With respect to A, order will be 2. With respect to B, order will be 0. All are second order rate laws. We can write down. Okay. I will choose to write down these integral forms. I will choose this first or this third equation. Here it is already in second order. Here also, this with respect to B, the order will be 0. The 10 to the power 0 is equal 1. Anything with respect to anything, if the power is 0, it will be 1. A to the power 0, it will be 1. Likewise, if 10 to the power 1, it will be 10. A to the power 1, it will be A. Likewise, here B to the power 0 means it is 1. So equation is dA divided by dt is equal Ka square. Okay. Now I will write down this equation. I want to integrate. To integrate, as I said previously, we have to move concentrations terms into left side and other terms into right side. So I will move this A square term into left side. Here it is as a multiply, but when we moving it from right side to left side, it will be a division. dA over A square, I moved it, and K, here dt I will move on to its right side. Here it is appear as a division. When it goes to right side, it will be a multiply, dt. Okay. Now I will put integration mark. Okay. After that, we can use the limits. Lower limit is A naught, upper limit is A. Here time, here actually before using these limits, we can simplify this equation further. How? This negative sign we can get out of the integral mark, dA divided by A square equal K. K is a constant, we can get out that, and dt. Okay. After doing that, we can substitute or we can introduce the limits. What will be the limits? Minus dA divided by A square, limits, and limits here K, sorry, what is the limits? Here initial concentration is A naught, final concentration is A. Here K, here T, what is the initial limits? 0 to T, time T. Okay. How can we integrate? In this situation, we have to remember another integral rule, power rule. If we want to integrate a power of something with respect to its variable dA, we can write down it as a to the power, that particular power, plus 1. Here I will introduce a common term n as the power, n plus 1, n plus 1. This is the answer of integral form of this a to the power n. We can integrate and final result is this. We have to add 1 and we have to divide n plus 1 likewise. At that situation, the a to the power 2 is appear as the denominator. So we have to rearrange this equation. We can put this a square as the numerator, but here it have a positive sign, a positive 2, power is positive, but if we rearrange it as the numerator, this positive term will be negative. Likewise this, here negative, here a minus 2 with respect to dA equal k t0 to t. Okay. A to the power minus 2. However, it is minus. We can introduce this power rule, minus sign. If we integrate this a minus 2, the result will be minus 2 plus 1 divided by minus 2 plus 1, whole are in brackets. We have to add limits. Here a naught to a naught to a, here k, here also we can simplify this. Integral marks will cancel out for d. Here also the same. Now it has limits, so we have to write down it within brackets 0 to t. Okay. Now we can simplify this equation. Minus, here negative 2 positive 1 mean negative 1 divided by negative 1, a naught to a k. We can simplify this term. We can substitute upper limits to this t, and we have to deduct lower limits k 0. Okay. Now how can we simplify this term? Left side. This a contain a negative power. We can transform it into a positive power if we put it as the denominator. So I will move it into the denominator, minus, here now a goes to down as the denominator, a power will be 1. I will not write down 1. However, it contains a negative sign because of this minus. Limits a naught to a equal kt, here kt because k into 0 is 0, here minus. Here you can see minus and minus will be, they are multiply, minus will be positive. Okay. Now its term will be a positive term now, 1 over a naught a kt. Okay. Now we can substitute these upper limits. What is that? 1 over a, we have to deduct lower limits, 1 over a naught equal kt. Okay. Now we want a term with respect to 1 over a. We want the integral form of this equation for 1 over a final concentration. So I will rearrange this equation. I will move this 1 over a naught part to right side. So I will get that equation as like this. 1 over a is equal to kt plus 1 over A naught. We will get this equation as the integral form of second order reaction. Okay. Okay, now this is your y equal mx plus c, m is k, x is t, c is 1 over A naught. Now you can see clearly 1 over A is y, k is your m or gradient. Now it is positive. In previous two cases it is negative. You saw that. T 1 over A naught, it is positive. Now you can plot a graph with respect to 1 over A versus time t. You know that the k is now positive. It has a positive intercept also. So graph will be like this. You can see. Graph will be like this, integral form of second order reaction. The graph is like this. Okay. Now what about its rate versus concentration? It is very important thing. If we plot a graph, rate versus concentration, this is second order reaction. Imagine here concentration, rate, here your particular thing A, its power is 2, second order, no? Okay, now imagine if the concentration is 1, its power will be 1, power is 2, is equal 1. If we double the concentration, its order is 2, the rate will be 4. If we increase our concentration by 3, twice, power is, order is 2, it will be 9. Likewise, it will increase drastically. So, if we plot rate versus concentration diagram, it will be like this. It increases rapidly. So, you can see the changes of with respect to first order and zeroth order. I draw every graph with respect to this integral form and rate versus concentration. Okay, now I will move on to half-lives. Before going to half-life, what can you say about the rate constant, unit of rate constant? K, the common equation, now you can remember that, molarity 1 minus n t minus 1. Here 1 minus n is second order, 1 minus 2 t minus 1. So units will be m minus 1 t minus 1. This is the unit of second order rate constant. That means that will be m l minus 1 dm likewise. Okay, let's move on to the half-life calculations. Now it is very easy for you, I know that. What is half-life? Here it is, initial concentration is A naught. After some time, final concentration will be half of initial concentration. At that time we call that spent time is T half. At T half, the concentration will be A naught divided by 2. That's the final concentration. We can substitute that into our integral form of this second order reaction. So final concentration 1 over A equal KT plus 1 over A naught initial concentration. We can substitute now. Instead of T, we can substitute T half. Instead of final concentration, we can substitute 1 A naught over 2. So 1 over A naught divided by 2 is equal to k T half plus 1 over A naught. We have to rearrange 2 divided by A naught is equal to k T half plus 1 over A naught. So, if we rearrange this equation, I will move this 1 over A naught part to left side. 1 over naught equal k T half. What will be the answer? Here 2, here 1. 1 over A naught is equal to k T half. The final answer will be T half is equal to, here denominator is A naught. Now here k will goes, here it is as a multiply, it will be a division here like this. So this is the T half of second order reaction, this equation. So you can see T half is now depend on initial concentration. If initial concentration is high, T half will be low. Now you can see that. Okay. In brief, I will explain what is pseudo first order reaction. We talked about zeroth order, first order, second order. What is pseudo first order? What is pseudo first order? There are two reactants, A plus B will produce products. If one reactant concentration is very higher than the other, if a reactant, one reactant concentration is very higher than the other, that concentration we considered as a constant, that higher concentration. Imagine like this, we do a reaction, there are two reactants, one is a solid, other one is here A, solution is A, here B. B is a solid, A is a liquid. The reaction going between these two, A and B plus products. So more B in this reaction. So its concentration is nearly, we consider the concentration of B is constant, because when reacting B, again this solid will dissolve and will release reactant. So the concentration of B will constant, we consider. So rate law, we will write down dA divided by dt is equal K A and B. At that time, please consider the all are first order. Okay, now K is a constant, we know that already. With respect to this B, we know A in the solution, A is a solution, its concentration is low, concentration of A is low, concentration B is very high, very high. With respect to A, B's concentration is very high. Because of that, we assume that the concentration of B is a constant. This also constant. So there are two constant. We assumed B also a constant because its concentration is very higher than the A. At that time, instead of this K and B, we introduce another constant, the A divided by dt is equal K dash. We introduce K dash instead of this K and B. So K dash is equal K into B concentration. So now the rate equation or rate law simplified as this. As you can see, the order is look like first order, but here in term K dash it included the concentration of B also, so we call this as pseudo first order reaction. Okay, that's a very small thing. Now I'm going to introduce you the summary of a zero order, first order and second order reactions. Let's move on to summary. Here zeroth order, here first order, here second order. In first order reactions, the rate is equal to K. In first order, it is R equal K A. If the reaction is A, will form products. With respect to second order, R is equal K A square. Okay. What is the rate equations? What are the rate equations? You can remember that here A is equal minus KT plus A naught in zeroth order. In first order it was ln A is equal KT minus KT plus ln A naught. Okay, what was the rate equation for second order reactions? That was very easy. 1 over A is equal KT plus 1 over A naught. It was very easy. What about the half-life? Half-life of zeroth order reaction was T half equal A naught divided by 2K. What about the half-life of first order reactions? It was T half is equal ln 2 divided by K. What about the half-life of second order reactions? It was T half was equal 1 over K A naught. Okay, so what was the rate? Units of rate constant. Here I introduced a common equation m1 minus n t minus 1. According to that, here in zeroth order n equal 0, so m t 1 t minus 1. This is the units of K. What about the first order? In first order, m 1 minus 1 t minus 1. Positive 1 and negative 1 mean m is here 0. What about this? Here m 1 minus 2 t minus 1. That means m equal negative 1. This is the units of rate constant of second order reactions. What about the graphs? According to this rate, what about the rates? Here rate versus concentration diagram. It was a constant in first order reactions, zeroth order reactions. In second order reactions, rate versus concentration was like this. What about the second order reactions? Rate versus concentration was like this. It increased gradually. If we here, it is always constant. It is obvious. Here, if we increase concentration by 1, it will be 1. Rate also 1. If we increase by 2, rate also 2. Doesn't matter. However, this in second order reactions, if we increase concentration by 2, rate will be 4. If we increase concentration by 3, rate will be 9. Likewise, it's increased very drastically. So, here it is increased gradually, here it is drastically increased, rapidly rocketed. That the rate. What about the equation graph for this integral form graph? It was a here t, it was like this, negative gradient. In here also it has a negative gradient, it was minus k, here ln a, here t, it also minus k gradient. What about here? It also has a positive gradient and positive intercept. All of this has positive intercept, that's why it has a positive intercept. However, here it has a positive intercept and positive gradient, that means its graph was like this. Okay, these are the main things you have to know when we comparing first zeroth order, first order and second order reactions. So this is the summary and other things. If you consider half-lives in zeroth order reactions, if we increase initial concentration, half-life will be higher. Here half-life is not affected by the concentration. In first order reaction, half-life is not affected by the concentration. Not affected. However, in second order reactions, the thing is opposite, because T half, it is inversely proportional to initial concentrations. That means if initial concentration is higher, T half will be lower. Those are the connections. So please keep those things in your mind, and this is the summary of chemical kinetics in this level, university first year and A level examination level. So please keep this in mind. Actually, these integral forms are not used in advanced levels. However, in university level, these are the basic things. Okay, after this video, I will introduce another video for biochemistry, the kinetics of enzymes. It will be another subject, biochemistry. So if you understand these lessons, please subscribe my channel and please share these videos with your friends, and thank you. Help me to help you.